Hello, Math Humans. We're going to do 3.1 today. We're going to be talking about extrema on an interval. Our objectives are that we're going to manage extrema, and then we're going to find the extrema on an open and closed interval. So from previous math courses, we want to talk about extrema. Remember that it can be an absolute, sometimes the words are global, max or min, and it could be a local or relative max or min. So for example, let's say I have a function and it looks like this, okay? So if I went from a -1 to 2, righty, this guy right here, this point would be an absolute minimum. And if we're talking about a closed interval, the endpoints like this would be, so I'm going to write the endpoints, which would be f of a -1 and f of 2 would be relative maximums. Okay, and then you would have to evaluate these 2 points to see if one is larger than the other to determine whether or not it's actually a maximum or a minimum. So then let's say I have this situation, right, where the endpoints are not included, and so that would be a -1 to 2 not included. Then all we have on this one is an absolute minimum. So the endpoints would not be included, therefore we would not have to consider their value. All right, the first definition we want to get today is the intermediate value theorem. We commonly refer to it as IVT, and this is the intermediate value theorem. This is one of those very important theorems. You will often use IVT as a justification for some of the math. Therefore, you want to make sure you have this on your formula sheet. The intermediate value theorem is an existence theorem, and it means that for a function f on a closed interval a to b, if f of a and f of b have a sign change, then we know that a 0 is going to exist in the interval from a to b. Okay, and we've talked about this before, but basically what the intermediate value theorem says, let's say this is a and this is b, right? And if f of a happened to be negative, and if f of b happened to be positive, then somewhere in the interval from a to b, there is a 0. Okay, and that's really all the intermediate value theorem says. The other theorem that we want to talk about is the extreme value theorem. So this is the extreme value theorem, and it is also an existence theorem, and it says if I have a continuous function on a closed interval, then f must have, oops, you can't see that, sad day. Now you can. Must have both a max and a minimum. Okay? So basically all that says is if I'm doing math on a closed interval, so let's go back and look at this guy. This is a closed interval. It says that on this closed interval, I would have a extreme value. The thing that is really important about the extreme value theorem is you must check the endpoints. Oops, spelled it wrong. So that's one of the most critical things about the extreme value theorem, is that you need to check the endpoints. So if we talk about math a little bit, so in previous math courses, so say in pre-calc, we learned to find extrema by using our grapher. So in pre-calc for extrema, we used our grapher. Calculus, though, is going to be way more fun because in calculus, we're going to look at what happens with the slopes. So let's say I have a slope that's increasing and then I have a slope that's decreasing. The point where that changes is going to be an extrema. Same thing over here. I have a decreasing slope and it turns into an increasing slope, and that is also going to be an extrema because it is where the slope changes. Another thing to notice about extrema is that at that point, I have a horizontal tangent, which means that the slope of the tangent line is 0. So those are kind of some cool things that we're going to talk about as we continue our discussion with extrema. All right, so let's talk about how to find extrema using some calculus because that's way more fun. So finding extrema. All right, the first thing that you're going to want to do is take the derivative. And remember that the derivative gives you the slope of the tangent line, which is also going to approximate the slope of the actual function. And then we're going to set the derivative equal to 0. So remember in the little picture I just drew, if I have an extrema, I have a horizontal tangent, which is why we set the derivative equal to 0. When you're showing your math, this is a really important step. So you have to show that you take the derivative, and you're going to do all that math, and then you have to show that you set that derivative equal to 0. That is a hugely important step because that shows that you understand that there is a horizontal tangent at the particular derivative. The second step is you're going to solve the derivative for x. And these are called the critical values. And this is going to be the location of the horizontal tangent. And then we are going to the last step, we're going to evaluate f at the critical point, and if it is a closed interval, we're going to evaluate the endpoints. And the reason it has to be a closed interval, it means that the endpoints are included. So let's start our first example. Okay, example number 1. I want to find the extrema of f of x is equal to 3x to the 4th minus 4x to the 3rd over the interval -1 to 2. Now, I haven't written it down, but the assumption is in calculus that you're going to do this using calculus and you're not just going to put it in your calculator and graph. If you did that on a test, on an AP exam, you would get 0 credit for finding the extrema. So I'm going to take the derivative. F prime of x is going to equal 12x to the 3rd minus 12x squared. And then I'm going to show that I set that derivative equal to 0. I'm going to solve for x, so I'm going to solve by factoring. And I'm going to get x minus 1. So I'm going to get x is equal to 0. And just for a reminder, it means that's a multiplicity of 2. That means that the derivative is going to bounce. And then I have x is equal to 1. So at this point, because it's on a closed interval, I'm just going to evaluate the function at the endpoints and at the critical values. So I'm going to start on the left, f of a -1, and I'm going to assume you can do this math. Notice that I'm evaluating the function and not the derivative. Okay, so I'm going to evaluate the original function at the critical values. So when I do this math, I get 7, and I'm going to assume you can do that math. And then when I evaluate the function at 0, I would get 0. When I evaluate it at 1, I get a -1. And f of 2, which is the endpoint, is going to be 16. And then this is pretty straightforward. The minimum is going to occur when x is 1. Minimum. There we go. And then this is going to be the maximum. Okay? So then if I answer the question, find the extrema occur at x is equal to 1, and in parentheses I'm going to put that it is a minimum. And then at x is equal to 2, and I'm going to put that it is a maximum. And that's it. And later they will ask more to go along with that, but for right now, that was all this question asked. All right, for our next example, so for example number 2, it says find extrema of f of x is equal to 2 sine of x minus the cosine of 2x on the interval from 0 to 2 pi. And again, this is a closed interval, which means that we're going to make sure that we test the endpoints. So the first thing I'm going to do is I'm going to start my derivative. So f prime of x, the derivative of sine is cosine, so I'm going to get 2 cosine of x. This is the chain rule. So I could rewrite cosine of 2x using a double angle identity, but I hate having to memorize that, so I'm just going to manage this with the chain rule. The derivative of cosine is a negative sign, so this is going to be plus the sine of 2x times the derivative of the inside, which is 2. And I'm going to rewrite that, so 2 cosine x plus 2 sine of 2x equals 0. So I've shown that I've set the derivative equal to 0. This is a critical step, and on an FRQ, this will be one of those things that earns you 1 out of 9 points just for showing that you set the derivative equal to 0. So now what I'm going to do to make solving this easier, if I'm doing it by hand, I am going to use the double angle for sine because it's easy. So this is 2 cosine x plus 2. The sine of a double angle is 2 sine x cosine x equals 0. Okay. And then I'm going to factor out a 2 cosine x. So I get 2 cosine x, and I'm going to get 1 plus. So then 2 sine x equals 0. Here are my two baby equations. I can set those equal to 0 and solve. So I get the cosine of x is equal to 0, and the sine of x is equal to a -1/2. Remember that cosine is 0 here and here, so x is pi over 2 and 3 pi over 2. Cosine is negative down here and here, and this is a -1 and 2, so this is 7 pi over 6 and 11 pi over 6. So x is equal to 7 pi over 6 and 11 pi over 6. Okay? The next step, we found all of the critical points, is to evaluate the function. And at this point, again, I'm just going to write the answers because I'm assuming that you can do this math. So I'm going to evaluate f of 0, and I'm going to get 1. And then I'm going to evaluate f of pi over 2, and I'm getting 3. And then I'm going to evaluate f of 3 pi over 2, and I get a -1. F of 7 pi over 6 is a -3/2, and f of 2 pi is going to equal a -1. So I got the left endpoint, the right endpoint, and then I got the 1, 2, 3, 4 other critical values. Remember, I'm evaluating in the function, not in the derivative. Okay? So as we look at our math, we can see that this is a maximum, and then I can see that a -3/2 is a -1.5, so this is a minimum. So I'm going to say f has a max of a max at 3. So f, the maximum is 3 f of 3. You don't have to actually show the value of the function, and that's where we tend to make mistakes, so you can just write f of 3. And f has a minimum at x is equal to, oh, sad day, I think I forgot a value. I did. Look at that. Shame on me. This is 11 pi over 6, and this is a negative 3/2. So then I have two minimums. At x is equal to 7 pi over 6 and 11 pi over 6. The minimum is equal to 7 pi over 6 and f of 7 pi over 6. And again, I would not take the time to evaluate that actual value. And then I have the minimum is at 11 pi over 6, and its actual value is f of 11 pi over 6. Alrighty, that is it for today. I will see you soon.